Okay, so today we're going to be going over some rules for exponents and logs. Um, you will see there is obviously going to be a relationship between our exponent rules, which I believe we know very well, and we're going to use that information to develop our rules for our logs. So if we look at our exponential expression, our base is 2, the exponent is x, and the power is 8, the value of the 2 to the x. Here, if we look over at our log equation, we have a base of 2, an exponent of 16, and the power, 2 to the 16, is the x. Now we'll start with our exponent rules. And we already looked at this one the other day. We had a to the m times a to the n would be a to the m plus n. And if we looked at a couple of examples, and then if we look now, logs are our exponents. What comes out of a log expression is the exponent. So we'll think about what is happening here. We have multiplication and we add those exponents together. So if I have log base a of m, and the same base, log base a of n, then I'm going to multiply those arguments, m times n. We do a couple examples. Let's say I have log base 2 of 3 and log base 2 of 5. That can be written, these two separate logs that are being added together with the same base can be written as log base 2 of 3 times 5, or 15. If we look at an exponent rule that we know very well, a to the m over a to the n, we can rewrite that with one base, a to the m minus n. We're subtracting the exponents. Do a couple of examples. 2 to the third over 2 to the second would be 2 to the 3 minus 2, or just 2. Likewise, 2 to the x over 2 to the 2x would be 2 to the minus x, or 1/2 to the x. Now again, the value of logs, what comes out of a log expression, is an exponent. We notice when we have these exponents here of our powers, we're subtracting them because we're dividing the powers. So when we subtract logarithms of the same base, we are going to divide the arguments, or the powers. So if I have log base a of m, subtract log base a of n, that is rewritten in one log expression as log base a of m over n. What's before the subtraction is the numerator. What's after the subtraction is the denominator, and I always make this like my fraction bar. We do a couple of examples. Let's say log base x of 4, subtract log base x of 2 can be rewritten as log base x of 4 divided by 2, which we could simplify as log base x of 2. Okay, another exponent rule is the power of a power rule. So I have a to the m to the n, and we know that we multiply those two exponents together. So 2 cubed squared is 2 to the 6th. If I had 5 to the x to the 4th, that would be 5 to the 4x. Power of a power. So likewise, if we have a log base a of m to the n, we can rewrite that as n log base a of m's. So that exponent on our argument can come out front and make a product, just like we had the product of the exponents. So I can have something, and it can go both ways. I can have 2 log base 5 of x and rewrite that as log base 5 of x squared. This is going to be my exponent. Or if it's more convenient, I could have log base x of a to the 7th. That could be rewritten as 7 log base x of a. So I can go up or come down. We have one more formula that we want to talk about for logs, and it's super helpful, and we will use this when we're going to be solving log equations shortly. This was very helpful in the day when there weren't graphing calculators that would give you approximations for log, common log, or natural log, or now any base. You had to go look at a table in the back of the book, but there wasn't going to be oodles of tables with all different kinds of bases. You had a table for either the common log or the natural log. So what you needed to do is change every log that was not base 10, a common log, or base E, to that base to evaluate it. And you did that using this formula. So we have log base B of A can be rewritten as the quotient of 2 logs in a different base. So we're changing to base C. And what happens is the base that I started with goes, what I like to say, in the basement or on the bottom. So base goes on the bottom of the fraction, and then that means the argument goes in the top. And a lot of times we will just use base 10 or base E. So we'll look at log base 9 of 16. If we want to change that to base 7, we write log base 7 over log base 7, and then we put what was in the basement, or what's the base in the basement, and then my argument in the numerator. If we want to change it using a common log, then we would write log base 10, or common log, of 16 over the common log of 9. And if we wanted to use our base E, we would take our natural log of the base divide into the natural log of our argument. All right, and then we want to go through some basic facts again. The log of any base, regardless of the exponent, if we are going to get an argument of 1, that's got to be the value of 0, because any base other than 0 with a 0 exponent will give us a 1. And we know log base b of b is going to get 1 because that's the exponent I would put on a b or any base to keep it, to not change it. And then finally, log base b of 1 over b is going to be the opposite or reciprocal. It's going to be -1 because b to an exponent of -1 produces that reciprocal of 1 over b. All right, so we're going to use those 3 facts, the change of base, and then our log properties from the front page to rewrite these expressions. And what we're doing here is we're expanding. We're going to go from one term to multiple terms. So if we think back to something that we've already done like this, would be doing our product of a binomial. We expand that product of binomials to go from those 2 terms being multiplied together to 3 terms being added. Same idea here. So we look at the structure that we have. I have a product. So that means I'm going to be using a plus sign. Those p's go together. And so then I have the common log of x plus the common log of y to the 7th. And then I have that exponent. So I'm going to use that rule that allows it to come out front. And now I have expanded from that one log expression to the addition of 2 separate log expressions. So going from one term to many. And look here, I have this division problem or a quotient. That means I'm going to be subtracting. This is my little visual for subtraction. So I will take the natural log of 9 and subtract off the natural log of y. Now this one has a bunch of stuff going on. We have a product in the numerator and a product in the denominator. But kind of the overall structure we have here is a division of 2 terms. So we want to address that first. So I want to take log base 4 of my numerator, subtract off log base 4 my denominator. Now we're going to address the product piece of it. So this product will be replaced with a plus sign. This product will be replaced with a plus sign. The thing we have to be careful of is to make sure that what we rewrite here goes into parentheses or brackets, because each one of those terms that are going to be associated with this expansion has to be subtracted because all of those are in the denominator. So let's break apart this product. I have log base 4 of 16 plus log base 4 of the square root of x, subtract log base 4 of 3 plus log base 4 of y to the 5th. Now we got some more work to do. This log base 4 of 16, I want to rethink this as 4 squared, that's 16. I want to rethink the square root of x as x to an exponent of 1/2. I want to distribute this, so I'm subtracting off log base 4 of 3 and subtracting off log base 4 of y to the 5th. And now I have a couple of exponents that need to be addressed, and I have that situation, log base b of b. All right, here's my answer. What exponent do I put on a 4 to get 4 squared? Well, this is worth 2. And then I bring that 1/2 out front. And then I have log base 4 of 3. Bring this one out front, 5 log base 4 of y. All right. Couple more examples here. This time we're going to do something different. This time we're going to do a process called condensing. So that's going from many log expressions to one. This is going to be a powerful technique for us to be able to solve log equations. And we want to do it one at a time. We want to take care of the exponent piece first. And then look for our structure for our division / products. So I notice here my overriding structure. I have to first check that I have the same base, and I do. I have base E. I have the subtraction of 2 log expressions in the same base. That means I am talking about a division problem ultimately. But I don't want to go there yet until I address my exponents. So I want to do this, and I want to do this. Then I can make my form. I have the natural log of x to the 4th y squared all cubed. This is your division bar over y z to the 6th all squared. Now we've got to use some properties of exponents and possibly do some simplifying. So my quotient here would really be x to the 12th, y to the 6th over y squared z to the 12th. And we notice we've got same base in the numerator as in the denominator, so we're going to operate with the exponents and have the natural log of x to the 12th, y to the 4th, all over z to the 12th. Okay, here I have a plus sign, so I have a product. And then what comes after this is going to make my division or my quotient. That's got to be in the denominator. Everything that comes after that subtraction, not anything before. We want to take care of our exponents first before we do any product quotient. So now I'm looking at common log of 8 to the 1/3 plus the common log of 6x squared. That entire argument is squared, not just the x, but the 6. So please use parentheses. Subtract the common log of, again, that 4y to the 16th. All of that is being exponentiated to the 1/2, or we're taking the square root of that. Would simplify this. That's my third root, so I could write this just as the common log of 2 plus the common log of 36x squared minus the common log of the square root of 4 is 2. I'm going to extract the square root out of y to the 16th and end up with y to the 8th. Now we'll address our product. So this condenses down to the common log of 2 times 36x squared and then now I'll take care of the quotient piece of it. So there's my division bar, and I'm putting my 72 Well, in fact, you know what? I'm not even going to multiply that out. I'm spying some common factors here. My numerator, everything after the subtraction is in the denominator. So I have 2y to the 8th. And now I'm going to reduce this quotient by dividing out any common factors. And I will get the common log of 36x squared over y to the 8th.